Thanks. Okay, over to you, Gil.
Well, thanks. Thanks so much, and thanks for having me in this seminar. I'm glad to be here despite the 7 a.m. at my place. But it will for a few hiccups during the talk because I forget what I'm supposed to say. So please be accommodating and ask questions when it happens, just to help it along. I hope it doesn't happen. Anyway, so the talk I wanted to give today revolves mostly around energy pumping in Weyl semimetals, but it has a bigger background to it, which is over the last 10 years, we really discovered, not we, but other people discovered a lot of interesting materials, particularly multi-layer Moire materials, like twisted bilayer graphene and twisted multi-layer transition metal dechalcogenides. And these materials have topological flattish bands and slow electrons. So topological flat bands, you can make correlated phases. I'm sure you heard a lot about this, but that's actually not my point. My point is that there's another thing that happens in this case. Velocity of electrons is really slow. In fact, can be slower than the speed of sound in the material, which makes for an interesting regime for electrons. In addition, Weyl semimetals play strongly in my mind as a new material that has unique properties. Oops, sorry. Make sure this stays. Unique properties in Weyl semimetal. In Weyl semimetals is perfect locking of the spin and the momentum relative to the Weyl node. So in the bulk of the Weyl semimetal, there's Weyl node, and around that Weyl node, the spin in 3 dimensions completely locks to the direction of motion of the electrons. There are many other new materials, and the question I think for us now is, what do we do with all these materials? They must be good for something, and we are in a unique position where we know the properties of the materials. We know what's needed technologically, possibly, and we can try to match the lines. What kind of things one could have? You could use new materials, particularly if they have small band gap, no band gap, spin orbit locking for far infrared detection. You can use them to detect even possibly entanglement, maybe dark matter. I stopped at far infrared, but I wanted to inspire people. But I know, dark matter. I wanted to advertise work by Ronnie Ilan and Catherine Zurek, etc. Suggested to use topological lead states to detect candidate dark matter particles along the same lines as one can detect far infrared light using such materials. You can think about the kind of devices that are electronics uses, like diodes and amplifiers. So isolators, rectifiers, or amplifiers. We have an infinite capacity for making such devices at small scale in semiconductors at room temperature. But there's very little that can be done in dilution fridge temperatures where electronics doesn't really work. And the only kind of devices that I'm aware of that can give you amplification are Josephson junction, so Josephson parametric amplifiers, Josephson traveling wave amplifiers. And the only way to get rectifiers is by, for microwave type superconducting circuits, the only way to get rectification is by interference. And if you're thinking about microwave, that means that rectifiers are fairly big in the scheme of any circuit design. Can we use new materials to overcome obstacles to such devices at low temperatures? Maybe. And I'm going to show you 2 examples of how we can utilize these properties of new materials to make unconventional amplifiers. So what are those 2 examples? So twisted bilayer graphene, as I was saying, has slow electrons. Could we use twisted bilayer graphene as a phononic amplifier? What's the idea? And this is work that was done by Ilya Essen, who's a postdoc at Caltech. You can think of setting up a device that has n-doped semiconductors n-doped semiconductor, twisted bilayer graphene, and then p-doped semiconductor, such that electrons tunnel from the n-doped semiconductor to the graphene to the p-doped, dumping energy, and that energy could actually go all into phonons, into terahertz phonons, and create an amplification and lasing medium. That would be a phaser. And I have to say, I have a bit of a healthy rivalry with my colleague Jason Alicia, and Jason and Kirill Stengel some years ago came up with the flux capacitor device, just as it was shown in Back to the Future. So I decided that at some point I need to also have a futuristic device, and this gave it to me, the phaser. That I won't talk much about it. I will concentrate on another idea for amplification. In valence semi-metals, you can actually get a topological amplifier. And this is work that was done with Ivor Martin, originally with Bert Halper, the initial idea, and Frederick Nathan, who was a postdoc at Caltech, is now back to Copenhagen, connected all the dots and showed how this topological amplification may happen in valence semi-metals. So that's my plan. First, topological amplifier. So I'll show you how synthetic dimensions arise from multiple Fouquet drives. And then I will show you how to use this principle to make a zero-dimensional Chern insulator. And from that, a topological frequency converter. And then I'll get to the possible realization in a doubly driven valence semi-metal. Any questions on the background so far? All good? All right, so let's start with synthetic dimensions. Oops, I see I did not correct a typo, and it's recorded. Ouch. Let's start with a simple driven Hamiltonian. So in this slide, assume a two-level system. H0, some static magnetic field, and then we're driving with some Pauli matrix times cosine omega t. I want to be in the slow drive limit. This is opposite than all of the Fouquet talks you must have heard. So I want the frequency to be smaller than the norm of the Hamiltonian. Now, in this case, I don't want to solve for the Fouquet states. I want to solve for the dynamics of the evolution. I just want to solve for the evolution of the wave function. And I expand it in harmonics. Now, take a look at this expansion. Psi t is e to the minus I n omega t, psi n of t. I did not specify that psi n of t has to be anything. This is a completely overcomplete way of parameterizing dynamics, but it's convenient. Why? Because I can plug this into time-dependent Schrodinger equation and then collect terms based on the harmonic, how many photons we took from the drive. And what you get is a Schrodinger equation that looks like nearest neighbor hopping. So the psi dt is the on-site Hamiltonian plus hopping plus the probability of absorbing a photon or emitting a photon. So it looks like a one-dimensional model, except a one-dimensional model in n space with hopping and on-site potential, except there's a potential landscape, right? There's a tilt in the model that accounts for the energy that the system takes from the drive. That's the idea of synthetic dimensions arising from drives. I think I didn't know this for many years, but then I heard from Arne Grimsmo the term Samba space. I think that's the same thing as Samba space. All right, can we get more dimensions? How about we do multiple drives? If we have multiple drives, we want to expand the wave function with multiple harmonics. Harmonics of drive 1, harmonics of drive 2. And then we can plug this into time-dependent Schrodinger equation. It's ugly, so I'm just going to have the graphic representation. You get an array. Sorry, what do I want to say? You get a two-dimensional space, n1, n2 number of photons we took from drive 1 and drive 2. And we get a tight binding nearest neighbor hopping dynamics over this lattice, but now with a tilt that goes in the direction of the omega vector, omega 1 in n1 direction, omega 2 in n2 direction. That's the potential landscape that makes sure that we conserve energy. Now, in this space, one may ask, how can the system move? And you know, a lot of times we hear the terms of when Hamiltonian is driven, we don't have conservation of energy. Actually, we shouldn't think about it like that. There is a conservation of energy. It's just that your energy can increase or decrease depending on how much work you got from the drive. In this case, if we have a finite bandwidth Hamiltonian, remember the norm of the Hamiltonian has to be smaller than larger than the amplitude, then you might not have room for taking too much energy or giving away too much energy. And because of energy conservation, you may actually be confined just to a strip perpendicular to the omega vector. And the width of the strip is the bandwidth of the Hamiltonian. And this is the same physics as Bloch oscillations. Right? If you have electrons in a finite band, electrons in a band with a finite bandwidth, and you apply an electric field, the electron cannot exceed the boundaries of Bloch oscillations, and those boundaries are given by conservation of energy. How much kinetic, the amount of work that the external field can do is limited by how much kinetic energy the electron can take, which is the bandwidth. And this is the same thing here. But motion in the perpendicular direction is essentially free. So this is, so what I showed here is that I can take a double-driven system and treat it like a two-dimensional lattice. Now you may ask, can I always do that? I don't know. Not a mathematician, but I think clearly one can at least draw the diagram. And then there's a more specific question, what is necessary to have an infinite space? And for that, omega 1 and omega 2 have to be incommensurate. The ratio should not be rational. However, if the ratio is rational, then the space will wrap around itself the same way that the lattice of a carbon nanotube wraps around itself, which restricts what momentum states the electrons on the nanotube can have, but the same kind of physics applies. All right, questions so far? All good? All right, please interrupt me. Just unmute yourselves, interrupt me. Just unmute yourself and mumble, and I don't mind. All right, so what I promised you is that I'll make a Chern insulator in 0 dimensions using this. So let me start with my favorite model for Chern insulator. That's the Bernoulli-Hughes-Chang Hamiltonian. And this Hamiltonian has sine px times sigma x, sine py sigma y, sigma x, sigma y Pauli matrices, plus a z component which has a static field, and the cosine of px, cosine py. We know that when m is smaller than 2b, this has a topological phase. Now I'm going to do the following. I'm going to take px and replace it with a winding phase, omega 1t. I'll take py, I'll replace it with omega 2t. And I'll do this consistently around the equation. And now I get a new Hamiltonian. That new Hamiltonian is actually a Hamiltonian for spin half that's driven by two elliptically polarized beams that are perpendicular to each other. One is polarized in the xz direction, and the other is polarized in the yz direction. But this is still a Chern band that's underlying this physics. So what will be the end result for that? One beam will do work, the other beam will receive work. One beam will come out depleted. That will be the pump. And the source, the other beam, will come in and be amplified. So I'll show you how this works and then try to apply it to Weyl semimetals. So this is the general scheme. You know, take your favorite band Hamiltonian, replace some of the momenta with phases as if the electrons in such bands are subject to a force, and the momentum changes linearly in time, and you get the properties that you had of the static Hamiltonian, hopefully showing up in the dynamics of whatever model you get, lower dimensional model you get. All right, so to understand this effect, let's start by recalling the anomalous Hall effect. So we know what particles do when they're in a magnetic field. We have a force that's given by a cross product of the velocity of the magnetic field. But something similar happens when you have Berry curvature. When you have Berry curvature, you also need to look at the velocity, which is given as the groove velocity in the band, plus an anomalous velocity term that looks like a magnetic field cross a velocity, but instead of everything happening in real space, it happens in momentum space. We have a Berry curvature that you should think in 2D points in the z direction, in the perpendicular direction to the plane, cross with a velocity of momentum, which is just the force. What is the Berry curvature? It is curl of something that looks like a vector potential, the Berry connection. And the Berry connection is given like so. There's a change of the wave function as you change momentum. And of course, the analogy is that this is the accumulated phase. This would give you accumulated phase for a particle being dragged through momentum space in some way. In the same way that the vector potential gives you the accumulated phase of the particle in the magnetic field as you drag it through space. Now, here's an illustration of how this anomalous velocity term works. It's not a simulation, it's just a PowerPoint animation. Here's the 2D Brillouin zone of a Chern band based on the BSD Hamiltonian. Berry curvature is concentrated around the gamma point. Here's real space. And let's imagine that we take an electron and apply a force to it in the x direction. Because of Bloch oscillations, because of the physics of Bloch oscillations, conservation of energy, the electron would not be able to veer too far in the x direction. However, the anomalous velocity term, can allow you motion perpendicular to the force that does not result in work. Every time that the particle in Brillouin zone will go through a high Berry curvature region, it can get displaced in the y direction. So here's the illustration. And this y direction motion can be accumulated. That gives you that anomalous Hall effect. So this reminds us of semi-classical motion of an electron in a topological band, hopefully. Now we're going to apply this logic to the synthetic dimension construction. So questions on this? Anybody wants to hear this review of semi-classical in more detail? You're good with this. All right, so moving on. So when we think about synthetic dimension, instead of x and y, we have this vector n, n1 and n2, the number of photons that the system, namely a spin half, took from drive 1 or drive 2. In n1 and n2 space, there's a Berry curvature. But I should say this, that let me say this in a slightly different way. Before we had a Brillouin zone that had px and py, and we shifted that Brillouin zone to be a space of the phases of the light. So px became omega 1t, py became omega 2t. But that's exactly as if we had an electron in a topological band, say a lower band in a two-band band structure that the Benedict-Hughes-Yang gives you. It has a Chern number. We apply a force in a direction omega 1, omega 2, and the particle starts moving in this Brillouin zone, as well as in the synthetic space. Now, in the Brillouin zone, we know already that we have Berry curvature. So every time that the electron, or every time that the system goes to a high Berry curvature region, it's going to move in the real space, in the n1 and 2 space, perpendicular to the force. And the force in this case is omega. But by doing so, it's moving up this red strip in a particular direction. It goes, the system loses n1 photons and gains n2 photons. And that's what I mean by frequency conversion or amplification. You're taking energy, you're taking work from one source and you're dumping it into the other source. So because the force omega 1 and omega 2 is in some direction doesn't describe a rational tangent. After this happens for a long time, the particle will cover the entire Brillouin zone. And when that happens, the total displacement along the strip would average over the Berry curvature in this Brillouin zone. And that will give you quantized energy pumping. So if you look at how much work source 1 does and source 2 does, it's omega 1. So source 1, it's the work that it does is omega 1 times the velocity in the one direction. But the velocity in the one direction is given by the anomalous velocity, which depends on omega 2 times the Berry curvature. Berry curvature averages to the Chern number over 2 pi. So this work becomes omega 1, omega 2, c over 2 pi. One of the sources is with a minus sign, the other one is with a plus sign, right? So source 1 in this example gives work, source 2 receives it. The amount of energy conversion is topologically quantized, omega 1, omega 2 times the Chern number. And that's the effect of topological frequency conversion based on work with Ivar Martin, Bert Halperin from some 5-6 years ago. Questions?
I have one. So, you know, okay. So, as far as I understood what you're saying, I mean, now this is the second time I think I hear this, so hopefully I did. This is dependent on the fact that the bandwidth is finite, right? Because you're sort of, that's why you can't accommodate as much energy as you want. So what happens if you were to couple, I mean, you're not just going to have non-interacting particles. What if I have interacting particles so that this bandwidth is not finite? Is it like there's a time scale, or what do you know, what is that?
Yeah, I think it really depends on band structure. So the first thing that one can imagine is that you have additional bands. And so I was taking a bite of my breakfast. So you can have additional bands. And this is the same for Bloch oscillations, by the way. So if you have additional bands, you can imagine that there's Landau-Zenner tunneling that happens every time that the electron comes to the edge of its Bloch oscillation. And this is the way that electrons can accelerate band structure, where they can get excited to higher bands and move faster, get excited to higher bands, move faster, and move sideways more. That's not about interaction. When you have interactions, you may get heating. There's no escape from that. But I see bigger experts than me in the audience for pre-thermal states, etc. So there might be interesting physics in interacting systems under certain constraints that will give you the same kind of behavior in a pre-thermal state. Now, what we decided to do is to think about a material that may realize this amplification. And there we encountered the same kind of questions and tried to control them. So actually the rest of the talk is about how exactly the issues of heating arise in Weyl semi-nanos. So true, in every practical application, there will be a certain amount of heating. And I think the game will be to have an amplification that's stronger than the heating. Now, this is a pristine principle. Never works like that in nature. So yeah, very good question. Other questions?
Sorry, Gil, can you elaborate a little bit on what's topological here?
Oh, that's a great question. So, and was asked before several years ago by Pete Brower a lot. So we had to come up with a good answer. So the underlying model is topological.
Yeah.
Right? This pumping arises because of anomalous velocity. But there's nothing protected here per se, it seems, right? So if I want to defend the term topological, I'll do it in the following way. So if you have a drive, so the upshot is, the end of the thought will be that the topology of the model protects against temporal disorder, against phase disorder of the driving lasers.
Mm-hmm.
And now I'll illustrate it. So if you have even omega 1 over omega 2 that's rational, that will be a situation where your synthetic dimensional space is finite, like a carbon nanotube. That quantizes which momenta the system can attain in the momentum space. So instead of having a series of lines that connect to each other through the boundaries and cover the entire Brillouin zone after some time, you'll just have a series of lines at equidistances, and the electron will constantly move on those. Right, so it would not actually sample the Berry curvature equally. It will just see the Berry curvature on some trajectory that's a measure zero of the Brillouin zone that is not representative. For practical applications, that might be even better because you can get a higher pumping rate than the topologically given one. But now imagine that the lasers have some noise in their phase.
Yeah.
Those finite set of lines is going to start moving around the Brillouin zone as a function of time.
Mm-hmm.
It will restore the quantization of the pumping.
Mm-hmm.
So that's how topology in this case
Mm-hmm.
It protects the topological long time average of the pumping in the face of disorder, even in lasers that are frequency locked in some way.
Mm-hmm.
So I think that's what I would say is the topological aspect in the dynamics.
Mm-hmm. Thanks.
Sure. No, we thought hard about this because obviously there's topological underlying principles, but there's nothing protected in what I'm saying. But there is this element of protection against temporal noise.
Mm-hmm.
Other questions? All right, so moving on, I really wanted to have a material, some idea of how to make this amplification principle into a device. And like I said before, the Hamiltonian that we had is basically a dot product of sigma matrices and a magnetic field of two light beams that are perpendicular. As always, when you drive a system, it's better to drive it with electric field rather than with magnetic field. And then if you think about this sine omega 1t, sine omega 2t as the electric field of a light beam or the vector potential of a light beam, then immediately we think about the Weyl semi-metal. The Weyl semi-metal has a Hamiltonian that's automatically around the Weyl node, the Pauli matrices dotted with momentum. But by minimal coupling, momentum is the vector potential. Just a better way of interpreting this in the context of the current work is that what we have here is the momentum of a particle minus the time integral of the electric field that's applying to it. And then if you dot that into the Pauli matrices to give the spin orbit locking, it's very easy to see how you'll get a Hamiltonian of this type. But in a real material, there are many, many electrons. Each one is going to do what they want, very small, but still have a mind of their own. They're going to mostly cancel each other. So for a Weyl semi-metal to be able to do this, we also need to think about a tilt of the Weyl node and anisotropy in the velocity around the Weyl node, and that's this extra term. Let's see how this kind of physics plays out in the Weyl semi-metal. So here's again the Hamiltonian of a Weyl semi-metal around the Weyl node. And now we submit it to two beams with a vector potential A1, A2. Here's a cut of the bend structure of the Weyl semi-metal along two directions with a tilted Weyl node and a whole Fermi surface. That looks elliptical, with many more holes on one side of the Weyl node and fewer on the other. Now we apply to this system, we apply these two beams, A1 and A2, one in the XZ direction, one in the YZ direction. And now you can plot what kind of a trajectory the electrons take in momentum space. So all electrons will take the same trajectory, but the initial point for them will be different depending on what momentum state they were in before the beginning of the irradiation. I didn't expect this, but I had Mathematica plot it. And what you get for two elliptically polarized beams in perpendicular directions is a bagel. But it's kind of like a Klein bagel. It turns on itself on two places. So the orientation of the surface here and here is opposite. It's like if this is a bagel, this is the sesame outside part, and this is the sesame inside part. And so I'll show you a better picture in a second. Now the physics is going to emerge from the question of whether the Weyl node is inside or outside the bagel. So let's see how this motion also reflects the pumping. So again, momentum becomes momentum minus EA. A is the two beams. And now we're looking at the velocity. It has a Benz group velocity part that we ignore. It's not important. And the anomalous velocity part. Here is the motion in momentum space that one gets. And one can imagine the Weyl node as a monopole that is inside or outside the bagel. Now, the work done by say field one is the electric field times the velocity of the electrons. But now the electric field is the ADT. The velocity, at least the anomalous part of it, is given by the Berry curvature cross the force. In this case, the force applied to the electron from the second beam. So that's dA2 dt. And by shifting around the triple product, we get omega Berry curvature dotted to the A1 dt cross the A2 dt. But we can shift from time to phase of the drives. And we get this TKNN-like integral, which really counts the phase. So A1 and A2 are the momenta of the electron in direction, and it's the contribution to the velocity, the contribution to the momentum change from the two beams. And this becomes the TKNN number of this Klein bagel with respect to the Weyl node of the material. So it's the Chern number of this given trajectory times omega 1, omega 2 over 2 pi. So this, to me, it's a little complicated, so I'll repeat some of it. We're thinking about a single electron. We irradiate that single electron with two beams, A1, A2. It goes into the electron goes into a trip around the Brillouin zone. That trip looks like this bagel. Then we calculate the work done by one of the fields, and we see that we get this TKNN form that integrates over the Berry flux, over the trajectory of the electron, over a long time. This becomes the Chern number of this shape times omega 1, omega 2 over 2 pi. That's how the spin-half physics gets manifested in the Weyl system. Just 1 second. Now, if you actually estimate how much pumping one can get if all electrons work together, that number is huge. So it's a third order effect in E, but it's not a perturbative third order effect. You need to have an electric field that's larger than the frequency in some sense. So it's a highly nonlinear effect, but at large fields, you get E cubed over frequency. And if you plug in numbers, like 1,000,000 volts per meter, which is very modest electric field, you can get to ginormous powers, a gigawatt per centimeter cube of material, if all the material and all the electrons cooperate. So it gives you an idea of the potential that this effect may have in a material where many electrons can work in parallel. So questions? All good? Okay, so this pumping is p-dependent, or k-dependent, in the sense that the trajectory of all electron in the Brillouin zone is the same but it's shifted depending on the initial location of the electron in the Brillouin zone. So you can have electrons that go through a trajectory through the three-dimensional Brillouin zone that misses the Weyl node, and that will give you a Chern number of 0 for that trajectory. You can have the Weyl node in the top part of the bagel, which will give you a Chern number 1, or you can have it in the bottom part of the bagel, which will give you a Chern number of -1. And you can also have this annoying situation of the Weyl node sitting on the trajectory. It means that the electron, no matter how strong the electric field that you're applying is, it means that the electron, those particular electrons go through a gapless point and are going to result in heating. They're going to be excited into a higher band and contribute to heating. So if you take all of this into account, as Frederick did, you get a map of pumping and heating. So here's the conversion power. It can be positive, it can be negative. And part of the, and it can also, and in this mapping, you can also get heating. You can also see the heating effect. So here's the conversion region where we convert positive. These electrons, so electrons in this region will go around the Weyl node with a particular, with the Chern number 1, they'll contribute to our pumping. Now remember, this is a whole Fermi surface, so this is the full part, and this is the empty part. Electrons that are found on the other side of the Fermi surface, think finite temperature, will pump oppositely. It will detract from the effect. And on top of that, electrons that are in this ring of fire region, where the trajectory takes them through the Weyl node, will again lose power and detract from the conversion region effect. In addition, there's spin momentum relaxation region. We're driving a metal. Metal will want to relax, and that would produce dissipation as well. And this recombination surface, as I said, fondly or unfondly called the ring of fire in this case, is where electrons go to the degeneracy point of the Weyl semi-metal and therefore get excited and eventually emit their energy, and it gets lost as heat. So Achilles was asking before about what happens when you have many body effects. In this case, we took many body effects in a very crude way. We just said there's one relaxation time in the material for all processes and simulated Boltzmann equation. So electron-electron scattering, electron disorder scattering, electron-phonon scattering, everything goes into one tau that allows relaxation of the electrons. And we were exploring within Boltzmann equation, what would be the amplification as a function of this tau. Now, I was going to say that, I wanted to say that this ring of fire dissipation is really crazy. It really destroys the effect. So if I go back to the previous slide, the dissipation from the Fermi surface, we can't do anything about. Ring of fire dissipation is stronger. And it would be really great to do something to counter it. And you can. So instead of having an irrational ratio between the frequencies, let's go into another limit. Let's go into the so-called Lissajous limit. In this case, when omega-1, omega-2 are rational, instead of having the full bagel, each electron takes a trajectory that's sampling with the Lissajous shape of this bagel. So just like, I don't know how many of you have done this, but probably all of you fed two frequencies that are rational into an oscilloscope and saw these nice patterns that emerge. So it's a three-dimensional version of those patterns. If you do this, if an electron goes through a Weyl node, it'll, how should I say this? Only the electrons with the Lissajous trajectory that goes through a Weyl node will get excited, and most electrons would actually miss the Weyl node. even if it so happens that it's on the surface of the bagel. So far fewer electrons are going to be subject to this non-adiabatic excitation point. And furthermore, the repeat time for those electrons to come back to the gapless point is much, much, much smaller, which means that they won't have time to actually decay and heat up the material as they would if they go through a Weyl node, go around it for a long time, energy, and go through it again. So that so instead of having this non-adiabatic dissipation, which is of the same order as the pumping strength that we were predicting, you get a suppression by 1 over the frequency of the drives times the relaxation time. And if the relaxation time is sufficiently larger than the frequency of the drive, this results in a large suppression of the heating, maybe 2 orders of magnitude. That's how we mitigate this heating effect. And it's always nice to slap another French name onto this kind of work. So, you know, Floquet has always been good to us. So here's another one. So before thinking about additional effects, we can see that we can suppress a big chunk of the heating by making the frequencies actually rational, which takes us away from the topologically protected region, one should say. Okay, now this is a material. There are more issues in it. And there's a big thank going to Cyprian Lewandowski for reminding us that real materials have real electromagnetic excitations like plasmons. And in this parameter regime that we're looking at, frequency and the chemical potential that are much smaller or smaller than the electric field amplitude. There are plasma waves in the material, and the plasma frequency in the Weyl semi-metal is very close to the chemical potential. It's always a fraction of the chemical potential, around a third. So we need to think about plasma oscillations that are also going to produce an electric field in any realistic device and push the electrons around. The dielectric constant is given by 1 minus the plasma frequency squared over the frequency squared. And if you factor this in, it can do one of two things. It can either suppress any electric field inside the material if this omega is large, but actually in regimes close to the plasma frequency, it can actually amplify. The plasma oscillation can actually amplify any external field. And this results in a, so this may allow you to actually amplify the effect if you match the plasma frequency with the frequencies of the drive. So as a function of chemical potential here, but for 2 frequencies that are set in the terahertz range, as you change the chemical potential, you scan through the region where the plasma frequency and 2 drive frequencies are very close to each other, and you can get a region where both the source and the pump beams are amplified because of this plasma oscillations, which is kind of neat. So now we can put all of these elements together and into a simulation that includes the electromagnetic effects, scattering, all in the Boltzmann equation. And what we get is the following. As a function of relaxation time, we can see what conversion power we get. Negative conversion power means we lose. You know, we may see an effect of 2 beams coming in at equal strength, one of them coming out weak, one of them coming out strong, but both of them are weaker than the source. That would be a nice topological physics exploration. However, if you really want a device, one of the beams has to come out bigger than what it came in, right, to get amplification. That would be a positive in this graph. If we take the irrational frequency ratios, it's very hard to get a positive balance. We'll need like 1 nanosecond relaxation time. However, in the Lissajous regime, you can go positive pretty quickly at around 200 picosecond relaxation time. So that's the limit that we find for Weyl semi-metals. Now you can ask about the linearity or non-linearity of this effect as a function of amplitude. So here's the gain, eta, Now notice the units are kilowatt per millimeter cubed, still imaginarily high power. And you can see that this is a highly nonlinear effect. As you change the electric field from small to large, you only get the positive gain effect starting at some finite field where the field exceeds the frequency by some amount. So a highly nonlinear effect, even though at this high electric field regime, it goes like E cubed. And now you can ask about the gain coefficient as a function of chemical potential for set frequencies. And this is the graph that shows the benefit of having the chemical potential matching the plasma frequency to the drive frequency. So if you're thinking about having a medium, while semi-metal light propagates through it, you can think of a gain coefficient. So per length, how much amplification you get. And you get tens, so tens per centimeter for the chemical potential that matches the frequencies of the drive if the relaxation time is sufficiently long. So I think that if you think about a device, you know, while semi-metal is a metal, so it'll screen light that goes through it. So the only active parts of a vial semi-metal will be around 100 nanometers around its surface. So you cannot make use of the per volume amplification, but you can make small grains of 100 nanometers size and array them. Now, in a regular regular traveling wave amplifier, a nonlinear optical crystal, lithium niobate or something like that, there's this issue of phase matching. You want to have your source and idler and pump all phase match in such a way that you get the right amplification. In this topological amplification paradigm, you don't need to phase match, but you can make an array that's resonant with the wavelength that you want to amplify. You can have the source going in one direction, the pump going in the perpendicular direction. You match the wavelengths of the pump and the source, and you can get directional amplification just like a gain medium in nonlinear optics. So that wraps up this idea of a vial semi-metal as a topological amplifier. And the big upshot, it would work if you have the right material with relaxation time in excess of 200 picoseconds. Are there such vial semi-metals? I'm not sure. The closest that we can think of is cobalt tin sulfur. And we were in discussions with Queen Narang for doing simulations. She helped us think about materials, so thanks to her. And I have to point out that there are many other works, interesting works on nonlinear optical effects in vial semi-metal, a lot of them coming from Joel Moore and Joe Orenstein's group. And with experiments by Joe and Darius Turoczynski. Other fantastic experiments from Ken Birch and additional works that try to probe similar effects to ours from Takashi Oka, who's of course a big hero in this field. So so this wraps up the part on the vial semi-metal. I want to spend another 3 minutes just outlining the phaser idea, but maybe I can stop here for a second.
Yeah, can I just ask quickly, so what's like your wish list for the ideal vial semi-metal for this?
Yeah, I think, so you want it to be anisotropic, but not necessarily type 2. You want to be able to dope it to small chemical potentials. And you want the relaxation time to be large. Now, relaxation time, probably interactions. So I don't know whether interactions factor into the relaxation time in a major way, or is it disorder, or is it phonons? My guess is that phonons are the biggest problem. So there's a calculation to be made to see under which conditions the phonon relaxation time at the temperatures of operation, which will probably be several tens of Kelvin, I think Frederick was telling me that in his simulation, the temperature seems to be around 70 Kelvin. You want the phonon relaxation time to be sufficiently long.
Mm-hmm.
So that requires, phonon electron coupling amplitude to be small. Now, I have to say, so I don't know whether Weyl semimetals would cut it. If you look in the literature, people report relaxation time for Weyl semimetals that go anywhere from hundreds of femtoseconds to hundreds of nanoseconds, saying that Weyl semimetals are super clean, etc., etc. Spin-orbit coupling protects electrons from scattering. Now, there's a question on which relaxation time we're talking about. So in our case, any knock to the electron in momentum space would take away the effect, even if the current relaxation time, the transfer relaxation time is long, this effect might be more fragile. So if you look at the literature, the ab initio literature, and ask what is the relaxation time of Weyl semimetal, it's hard to tease out an answer that I can trust for this particular effect. So I decided to wait and not do the total ab initio calculation to figure out whether this effect can actually happen in the Weyl semimetal, but rather use this to show how the material can actually be used, and use this as a first shot at a platform that can do this topological amplification, and maybe be inspired to find better materials. And there are better materials. There are other materials that can have similar effect. And one thing that my group is working on, and this is Etienne Lantano-Bis and Ortubis and Ilya Essen are working on, is the idea of rhombohedral graphene. So multi-layer rhombohedral graphene may show similar physics. So I think there's several materials that can show this physics. One of them, in a regime that's applicable. Weyl semimetals seem to be more in a regime that's interesting for physicists, namely, can you see this dynamical topological conversion? You probably can, but in a too lossy way that would not be useful for a device. So yeah, I think my personal hope is that people like Ken Birch or Nugetic would actually do the experiment, or there is Stochitsky would actually do an experiment to see how far Weyl semimetals can go in this kind of driving regime. All right, does this answer your question reasonably?
Yeah, sure. I know nothing about Weyl semimetals, so it's just for my general culture.
No, so I think Weyls are close, tantalizingly close, but not close enough to start a company. Other questions? All right, so I'll quickly flash the other idea, if I may. So Ilya and I were trying to think about ideas inspired by free electron laser, where you have a Wiggler array of magnetic fields. They shake the electrons produce a high energy laser beam, and they travel in it, and somehow they resonate with it and produce a really powerful laser. We thought there were some ideas in the literature to do that in graphene, using synthetic magnetic fields in graphene. But we were thinking, well, in twisted bilayer graphene, you can use the fact that the velocity of the electron is smaller than the speed of sound to amplify phonons rather than light. And as I said in the beginning, the idea is to sandwich with twisted bilayer graphene with an n-doped and a p-doped semiconductors, such that electrons go from the high energy states in the n-doped semiconductors into excited states of the twisted bilayer graphene. Still, flattish band, low energy, but still high momentum states. They can decay into low momentum states and then be absorbed into the p-doped semiconductors into the top of a hole band or something like that. So this would produce a population inversion. And the hope is that the energy that the electrons emit will go coherently into a phonon beam that will be amplified in this. How can you do that? If electrons are slower, the dispersion lies, if electrons are slower than sound, the dispersion lies lower than the acoustic phonon dispersion. If an electron wants to relax, it's missing momentum, it has too much momentum to give than the phonons can take for the same energy. But you can make up for the momentum difference by making an oscillation in your material. And that oscillation could be due to a modulation in strain, or it could be because of an array of gates. The length scale we're talking about are many tens of nanometers. So in terms of fabrication, it should be possible. And then we calculated the gain of this medium. And here's a graph of the gain that one gets as a function of frequency. Again, this targets the terahertz regime, which is always hard to control. So far, there's a gain as a function of x, which would be given as, okay, so gamma 0 is 10 per micrometer, and the gain that we'll get would be about 10 to the minus 2 per micrometer. So if you have a centimeter, you can get an amplification of 100 in such a device. So this example, I want to say, yeah, so this example is a way of utilizing the slow electrons in a flat band material to actually give you an unusual gain medium for phonons. And summing up, there's the final device we want to make, and this is a good time. There's the phaser in its final form, and this is a good place to stop. Thank you.
Okay, thank you very much for this